Hello guys, how are you?
Hi.
You feel good after the exams?
I still have 2 more coming up next week.
Yeah, including mine or different?
Including yours, yes.
Okay. Okay, so as I mentioned yesterday, you see the announcement. So this lecture will be, I will give you some hints about guidance about the homeworks. And any one of you has a question, of course, I will be happy to answer. Okay. So first, let me share my screen. This is a new computer, so I have some problems with it at this moment. I don't know why it acts so weird. So Zoom should be same everywhere, but here it's different. Okay. Okay, so let's share the screen. You can see the screen, right?
If it's OneNote, then yeah.
Okay, yes. Okay, so the via obstacle function in the RRT and PRM homeworks, okay, basically to check if you have an obstacle between two nodes. So basically, this this function receives the map because the map array contains the information about each cell, if it's free or has an obstacle, okay? And also receives point one, or let's say the new point, the new nodes that you generated and you are checking around, okay? So let's call it, I think I'm calling it new X and the new Y. So these are the coordinates of this node, this point, okay? It also receives the parent, I'm sorry, not the parent, the neighbor that we are checking against, okay? Not parent. Again. Neighbor, not parent. Neighbor. That we might connect to. Of course, it will be a parent if this is, for example, the minimum distance in PRM, okay? So let me call it I am calling it what? Neighbor, yes. Neighbor X, neighbor Y, okay? And we should check if there is an obstacle between these two nodes or not. So let's assume we have these two nodes. Here is a node, here is another node, okay? Here is the new point. Okay, so this is new X, new Y. Here is another point in the coordinates, neighbor X, neighbor Y. Okay, and you want to check if this edge here is crossing an obstacle or not. Okay, so the basic idea is that you don't know where if we fix this point, for example, and make it, for example, as like origin for us, okay, or frame of reference, then this point may be everywhere. Maybe, for example, it may be here, maybe here, or it may be here, okay, somewhere around. The solution that I will explain to you is a general one. It varied whenever this point is, okay? So let's take this, I'm gonna use this one because it's easy to visualize. So let's omit this edge here, okay? And so this is neighbor X and neighbor Y. Okay, so we divide it into segments. Okay, so we're gonna imagine just points. For example, let's divide it into 8 sections. So we will check this point if it's an obstacle or not. We will check this point. So let's call it 1, 2, 3, 4, 5, 6, 7. So we divided it into 8 segments. So 8 segments has 7 points. Always the number of points that you're gonna check is equal to the number of segments minus 1. Okay, and just to forget about these segments, just look at the point. So I'm gonna omit even those segments and just look at the points. And we will assume that if all these points are not belong to any obstacle, then there is no obstacle between this node and this node. Okay, so let's here, draw a horizontal line like this, and then a vertical line. Let's imagine this situation. If I want to move, from this point to this point, okay? So what will be the change in my coordinates? So I'm standing in here now, in this point, and I want to move to this point. So what will be the change in my coordinates? I will move this distance in X, then this distance in Y, okay? So if I want to move directly like this and stop at some points, which are these points, so let's relate the coordinates of this point to this point here. Okay, so if we just draw vertical lines like this, we're gonna notice something. There is another point here. That the number of points on Y is also 7, and the number of points here is also 7. It's really ugly. So let me draw it nicely. Sorry for this. I will draw it in a bit bigger to make it more clear. This point here. Okay, now it's bigger. And let's have, just 3 points to make it more clear for you. So let's forget about the segments and just concentrate about the point. Okay, so here is the horizontal axis that I was talking about. Here is the vertical line. Okay, so I know the coordinates of this point and I know the coordinates of this point. And I want to move from here to here. Okay, if I'm gonna pass by these points, there will be a change in my coordinate. If I'm standing in here and I will move in that way through these points, okay, until I reach here, there will be a change in my coordinates. Remember, our unknowns now are this point in between. If we know the coordinates of this point, then we can say, for example, map of, for example, x1, y1 of x1, y1. We're gonna check this value. If this value is 1, there is an obstacle. If there is value is 0, there is no obstacle. Okay. So if I move from here to here, if there is, for example, new x and new y, okay, so x1 is actually equal to new x plus this distance. Okay, let's call it d plus d. And y1 is equal to new y plus, let's call this dx, and this is dy and dy. Okay, now if I know dx or dy, I would know x1 and x2. So we know the number of segments. Okay, for example, here the number of segments is 5. 1, 2, 3. I'm sorry, 4. 1, 2, 3, 4. So the number of segments is 4 in here. Okay. So when I divide this distance from this point to this point in here into 4, I'm also dividing this horizontal distance also into 4, and also this vertical distance into 4. Okay, so actually dx is equal to neighbor x absolute of neighbor x minus new x. Minus new x. This is dx. I'm sorry, over or divided by segments. And dy is something very similar. Absolute of neighbor y minus new y divided by the number of segments. Okay, so all these distances, of course, they should be equal, but the drawing is bad. So this distance, or this distance, or this one, all of them are dy, and all of them can be calculated using this. Just subtract the neighbor y minus this y, the new y, and divide it by segments. This will give you dy. Okay. So if this is x2 and y2, what should be x2 and y2? x2 and y2 is again new x plus 2 dy, and here is new y plus, 2 dx plus 2 dy, and x3 y3 new x plus 3 dy y3 new y minus dx plus 3 dy. Okay, once you know these points, the coordinates of these points, you can check using the map array. Okay, remember these points are cells in the map array. They might be 1, they might be 0. If they are 1, then they are part of some obstacle. If they are 0, then of course they are free. Okay, now the location of this point might be, as I said, might be in that here or here or here, around anywhere around your point. This one, the new point, which will make it just like an origin for us. Okay. So we want a general solution. So in here, if we assume that this direction is the positive x direction, and this direction is the positive y direction. So what will happen to x1? Does x1 increasing, or I'm sorry, higher or lower than new x? Can anybody answer this? Have a guess?
It's higher.
No, it's lower. So this is, okay, this is, oh, I'm sorry, yeah, that's higher. I'm sorry, yeah, that's higher, of course, yeah. And how about y1? If this is the direction of the increment of y, is it higher or lower? Does y1 greater or than new y, or new y is greater than y1?
Y1 is greater.
That's right. Okay. Now, the question is this solution is general or not? So let's now check this one. If the neighbor is in here, okay? If the neighbor is in here, we will have something like this. Let's do it with another color. So this will be the edge. This will be, this imaginary horizontal line and vertical line. And again, we're going to divide it into 4 sections or 4 segments with 3 points in between. And still, these are the positive directions of y and x. So let's say this is x1 dash and y1 dash. So what is the relation between x1 dash and x new x? Is it higher or lower? Should I put here larger or smaller? Which one?
In that case, isn't it smaller?
Yes, it will be smaller. Yes, that's right. How about y1 dash?
That one would be greater.
That's right. Yes. Okay, let's see now, check if our equations will do that for us or not. Okay, I am saying that x1, of course, this should be a general equations. Okay, you apply it whatever the point is, obliviously, we can say. So x1 dash should also equal to new x plus delta x, right? So new x is in here, okay, but I shouldn't add, I should subtract, right or wrong? I should subtract or add? Somebody answer me.
Shouldn't you still add it?
No, because we are saying that x1 dash is less than new x, right?
Oh.
So x1 should be something, new x minus something, not add. So it should actually equal to, so let's do it. So x1 dash should be equally new x minus this distance, which is dx. Okay, so a better solution or a general solution actually is to eliminate this absolute. Okay, and just take whatever value you have with its sign, and let's check that. So if now new x is, this is the neighbor now, so here is the neighbor x and neighbor y. In that case here, neighbor x is less than new x, and the neighbor y is greater than new y. Okay, so if we apply this equation, this one here, neighbor x is less than new x, so this will be negative, right? So let's take all the situations. Let's take all the situations. We're gonna make it. So this is our new x and new y, and here is situation 1. Okay, so this is I will call it nx and ny, just to make it more concise. This is situation 2. Okay, nx, so nx1, ny1, nx2, ny2. Situation 3, nx3, ny3, and situation 4, nx4, ny4. Okay, and the equation is as follows. The equation is delta x equal to neighbor nx in general minus new x over segments, and dy equal to ny minus new y over segments. Okay, here is x is increasing, here is x is decreasing. This way y is increasing, this way y is decreasing. Okay. Let's try, or let's first check this quarter here. Okay, here ny1 is greater than new y, and nx1 is greater than new x. So we want to do something like this. Nx, we want to add actually. So here we will add dx and we will add dy. To move from here to here, we should add to x and we should add to y. Let's check this. So the equation is x1 equal to new x plus dx, y1 new y plus dy. Let's see if this is satisfied or not. Okay, so x1, for example, let's draw something like this. Let's assume it's just two segments with 1 point. So this is x1 and y1. So x1 is equal to new x, should be plus dx, plus something. Okay, so let's check if the x is positive or negative. nx, which is this one, nx1, and the new x is here. Okay, so nx1 is greater than new x, so this will be positive. How about y1? y1 is equal to new y plus dy. So y1, this y is equal to y, new y here, plus this distance dy. So it should be positive. It should be added. Let's check. dy is equal to ny, which is in this case, in quarter one, ny1, minus new y. And new y is less than new y1. So that ny1. So that this will be positive. So we're really adding in here. Okay? Let's check quarter three. So this is with quarter one. Let's check quarter three before quarter two. Okay? With quarter three, we will move in this direction. In this direction, x is decreasing. And for y, it's moving, it's like in this direction, and y is increasing. So nx3 is actually less than new x. ny3 is greater than new y. Okay? So we won't subtract. So let's assume again, this is x1, y1. Okay? So x1 is actually equal to new x minus something, minus delta x, this distance. So this should be negative. So let's check that. dx is equal to nx, in this case nx3, minus new x. And this is, this is nx, this is the point, and it's behind new x. So it should be less in the way of negative, or in the way of reduction of x. So nx is less than new x, so that will be negative. So here the dx is negative. How about y1? y1 is equal to new y plus something, because I'm going upward. So it should be positive. So let's check that. dy is equal to ny minus new y over segments. ny, in this case ny3, and it's above new y. So we in the direction of the increment of y. So this means ny is larger than new y, so that this will be positive. Okay, so till this moment, we can use these two equations with these current shapes with this quarter and also this quarter without any change. How about number two? So we will move in that way with number two. So this is below this point, so y should be reduced. This is the direction of the decrement or the decrease of y. But it is in the way of the increment of x. So here, nx2 is greater than n new x. So dx should be positive, and we're going to check this. And ny2 should be less than new y. So when I move from here to here, for example, this is x1 and y1. So x1 is equal to new x plus something, plus dx. And I'm sorry. And y1 is equal to new y minus something, minus dy. Okay? So let's check if this is correct again or wrong. So we know that nx2 is greater than new x. So dx is equal to nx2 minus new x. And nx2 is greater than new x, so this will be positive. So that's really adding, like what we are expecting. How about dy? dy is equal to ny minus new y. ny2 is less than new y. So this will be less than this one. So this will be negative. Okay. And that's exactly what we want. The last one, this is to the left of new x in the direction of the decreasing of x. So x is decreasing, so nx4 is less than new x. And also it's below new x and dy. So ny4 is less than new y. So if this is x1 and y1, to move from new x to x1, we should subtract something because we are moving in that way. So x1 is equal to new x minus something, minus dx. So let's check if dx is really negative. So dx is equal to nx minus new x. So nx4 minus new x, it will be negative because nx is less than new x. So this is really negative. Y also should be negative because y1 is equal to new y minus something because we are moving in the negative x direction, in y direction, I'm sorry. So dy here should be negative as well. So let's check that. So we know that ny4 is less than new y. So dy is equal to ny minus new y. ny4 is less than new y, so it's also negative. So both here are negatives. The conclusion is you can take this equations and apply it whatever these four equations and apply it whatever the location of the point is. And negative or positive subtract or add will be compensated by itself, okay, because we didn't add absolute here. So whenever you want to add dx, you will find dx itself is positive. And whenever you want to subtract dx, you will find that dx itself is negative, and the same for dy. Okay. So basically, in that function, you send the map, you send the new x and new y, and you send neighbor x, neighbor y. Okay, and of course the number of segments. Then you calculate dx and dy using these two equations. Okay. Then you calculate, let's call them xn and yn, where n is from 1 to, number of segments minus 1. Where xn is equal to new x minus, or I'm sorry, plus, because we said that the minus or negative will come from the equations of dx and dy. Plus what? Plus n, we can, yeah, n, yes, n dx, and yn equal to new y plus n dy. Okay? Or these equations, we can say. Yeah, one important step here after calculating xn and yn, you should check if there is obstacle there or not. So the check is something map of xn, yn. But here is some caveat, because usually because you have a division, so you have decimal numbers because you have a division here. Okay, so you should take a floor of this floor or round. So we should round both xn and yn before checking in that check. You can't say map of 1.1 and 2, for example. You can say map of 1 and 2, or even 2 and 2, okay? I usually go with the floor, and the floor is okay. If you want to make a rounding, so you can round up or down based on the decimal number. So for example, 3.4 will be 3 and 3.6 will be 4. It's up to you. Both will work. Okay. Any question, guys? Did I make it clear for you, or so for example, my lines of code for via obstacle, it's exactly 14 lines. But I am dealing with xn alone and yn alone. You can, for example, combine them together because MATLAB is very powerful when dealing with arrays. So you may make this these two lines here. This is actually like 2 lines. You can make them in 1 line. So you can reduce, for example, here, if you do that, so this will be 1, 2, 3, 4, 5, 6, 7, 8. It will be 10 lines. Okay. Yeah, like what Dominic say. So floor of something, you take the floor, you go down. So it's a 5. Floor of 5.99999 is equal to 5 as well. Okay, seal, as Dominic said, always, so this is going down. Seal is always going up, so this will be 6. Okay. Round, there is a function called round, but I can't remember what. Let me check this. Yeah. There is also round, and round, what we'll do. Let me check round of 3.4, 3.5. Yeah, round. So if you want to use round, let's do it another slide. Round, it checks the decimal point, the decimal number. So round of 3.4 will be equal to 3. Round of 3.5 or more than 5 will be equal to 4. Okay. Yes, it's better to use round. Okay. This is clear, guys, or not? Anyone has a problem? Everything is good? Okay, so this was for so the other construct route in RRT homework. So I asked you to construct the route, which is really easy. Okay, so you will end up with an array like this in RRT. So you have the graph array. So let's have here some tree. Okay, it's 1, 2, 3, 4, 5, 6, and 7. And let's assume that this is the start and this is the goal. So here 1 has no parent, so this is a node, and this is the parent of this node. Infinite. Infinite means no parent. The root of the tree. 2 has 1, 3 has 1, 4 is also 1, 5 is 4, and 6 is 5, and 7 is 6. I'm sure you know this, but let's do it also. So here basically, once you reach the goal, which is 7, you start to construct the route. So you check the parent. That's it until you reach the start. So while parent doesn't equal to the start, you will do this. So parent equal to, I don't know, array. So the array, let's call this is the array. So this is the array of the current parent and 2. That's not good, by the way. I don't want to write a code because it will be difficult. If you implement it in the same way as I am writing, it will be bad. So it's better to say it, just like a pseudocode or something. So check the parent of each node starting from the goal. Okay, in that way. So parent of the goal equal to 6. Then you check the parent of 6. It is 5. Parent of 5. 4. Parent of 4. 1. And 1 is the start. So you end up the while loop. Okay. You guys want me to explain more about this, or it's clear?
No, it's clear. I just had a quick question. For the function, I see that you input map. What exactly do you want us to do with map?
Where? Which one?
For the construction route, the function on MATLAB, you're inputting map, right?
Mm-hmm.
What is this for? What is it used for? Because I did it like without using map, but I'm wondering like.
Yeah, I understand. Okay, I got it. I got you. Let me check again. Yeah, you are right. You can do it without map. So you're absolutely right. You can do it without map. I'm just, sometimes I'm adding because it's not it's not harmful to add inputs to any
Yeah.
to the function, so that if you need it in the future, now you may use it, but maybe you have some difficulty and you want to check something, then you may need it in the future. So I just send it. If you have if you got something to do with it, use it. If you don't, you are not losing anything. So that's why I just kept it there. But you can,
I have a question. So do you just want us to leave map in there, or do you want us to take it away?
It's up to you. That's fine for me.
Okay.
Take it away. That's fine.
Okay, thank you.
But take it away from both. When you call the function.
Yeah, I know.
Professor, I just had a question trying to understand tree connections.
Mm-hmm.
So basically, tree connection contains like all the nodes along with their parents in the second column. But I'm trying to look at the graph on my MATLAB, and how do I know which one's the goal node in tree connections? Is it the very last entry?
So the goal node is given before the while loop. Of course, it's one of the inputs to the. It's not like PRM. In PRM, there is no goal or start. Okay, it's the second phase that we didn't touch it. We will touch it probably after 1 week. Okay, so the first, I'm sorry, in RRT, the start and the goal nodes are part of the inputs. Okay, and whenever we check that the new node is close enough within some distance to the goal, then we try to connect the goal to that node, to the last node that we generated, last random node,
Mhm.
and it will be the parent of the goal. Okay, and from this point, you end up the construction phase. Then because now the array contains, or the graph or the tree contains the start and the goal. So we have enough information to construct the path between the goal and the start. So
Okay.
let me share the other screen with you. You guys see the MATLAB?
Yes.
Okay, so let's go. So as I said, goal is one of the, where is the goal here? Yeah, is one of the inputs. So here we generate a new node. We try to find or locate its closest neighbor. Then we connect to it, connect to the closest neighbor. And then we are checking if we close to the goal. Okay. So in here, this is the step. So if the goal node is within the range, if the distance between me and the new node that we generated and the goal is within the range, the maximum connect length, I'm sure you know it because you submitted your homework, right? So yeah, then if this is right, then we connect the goal to this new node, okay? And that's it. After that, we construct the path.
Okay. And in
And yeah,
oh, sorry. In tree connections, professor, that's all the IDs, right?
in the three what?
In tree connections, the what's
You
stored
mean
in there?
this one?
Yeah. It's the ID that's stored in there, right? Of the nodes.
Yes,
Okay.
it is ID. But look, the ID is, you will find it a very big number.
Yeah. Okay.
This is because you have 1300 by 1300 array.
Hmm.
Okay, so for example, the node at column 1300 and row 1300 will have an ID equal to 1300 by 1300.
Hmm.
Okay, which is more, it's 1,600,000, something like this.
Okay.
So it will be very big. Okay. You have question, guys? Other questions? That should be easy assignment. Really easy, especially the second one, because constructing the route, we do that all the time. You know, it should be called the construction route, of course, because I do the robotics and you do the construction route. Okay, so okay, we don't have questions, so let's go to the late two homework. So actually, I shipped my new computer. I'm sorry, the last computer, my previous computer, to be fixed. So the code is up there, but I will try to to remember with you. So the problem was to light the LED, right? LED two, to light LED two. What was the? I have the assignment. Okay.
It was to make it blink red and then green. And
Yeah, I will open it now. Okay. Where is it? You got problems with this one? What kind of problems you have with this, or you had? I mean, even if you have a problem, then you fix it.
With LED2, professor?
Yeah.
I don't I have a question, but it's more of after class I was wondering if you could look on my code because I just have a question on one part on it.
Okay. So let me give the idea very quick. So we wanna, you can see the tablet, right?
No, we see your screen.
Okay. So let 2 is actually a structure, has a structure like this. It's very nice. And all of these are in, so this is, the MSB 432 B401R. Okay. So that's the experience of 3 months. Okay, so this is B1. You guys remember which board? I could B which pins?
It was port 2, pins 0, 1, and 2.
Thank you very much. Okay, so and these 3 LEDs are contained in one package. Okay, one is lighting red. Yeah, this is green, and this is blue. Okay, so for example, if you want only red, you send 1. So for only red, you send 1 on 0, and 0 on B21, and 0 on B22. Okay. If you want, for example, yellow. Yellow is a mix between red and green. Since these are in the same package, okay, so when you light 2 of them at the same time, you will see the mixed color. So here we want yellow, so you turn on the red and turn on the green at the same time. So here we send B20 equal to 1, and B21 equal to 1, and B22 equal to 0. Okay, and so on for the other ones. So basically, first we to set up this our board 2 in that case. To set up board 2, what we want the microcontroller to define this board as a GPIO. So these pins in specific. So I'm talking about the first homework, LED 2, not the second one that is a bitwise one. So you can do something like this. B2 cell 0 and B2 equal to 0. So all the bins of, including of course our the bins that we're interested in, which are B2.0, B2.1, and B2.2. All of them will be GPIO. Then you should inform the microcontroller which direction they will be used. Is it input pins or output pins? So here we want output pins. So the B direction register. So this is board 2. Oh. The second step here, the direction. So the direction you want something like this. So let's as a comment, you want the direction register to have this number. So this is 7. Okay. This is the setup. Now the microcontroller knows that B2.0, B2.1, B2.2 are GPIO pins and they are output pins. So it will send signals through these pins. Okay. Now for the function itself, it will be while true or while one. Okay, I'm not sure if there is something called true in C or not, but we are sure that one is working. And what you're gonna do, you have counter, some let's call counter called j. So int j equal to 1, and you say if j, I'm sorry, yeah, if j equal to 1, something like this. Okay, then you want, for example, red. So this is for red. So if j is equal to 1, so b2 0 equal to 1, b2 1 0, and b2 2 equal to 0. Okay, then you increment j as well. Then you make a for loop. Okay, and once this for loop is finished, then you do the other color. For example, actually we don't need this. We don't need this. So we don't need the other counter. You can do that in that way. Yeah. Then you do another color. So for example, red first. Then for example, yellow. So here b2.0 equal to 1, b2.1 is equal to 1, b2.2 is equal to 0. Then you do again the for loop. Okay, then the other color until finally the white. I think the last one is white, in which all of them are equal to 1. And you have the for loop, and you end the while loop. Okay. If you didn't do that in do it in that way and it works with you, that's fine, because you can do it in many ways. Okay. But this should be the general idea of it. Okay, guys. This is clear.
Yeah, Professor.
Okay. Anybody has a question?
Yeah, I had a quick question for the other homework. For lab 3, for the bitwise.
Yes.
Yeah. Is there a way to iterate through hexadecimal, or you have to hard code it?
When you need this. But no, but why you need to iterate through hexadecimal?
No, because
you mean this iteration? Let me ask this. You mean this iteration here?
No.
Yeah.
Because for this assignment you're talking about, I just did a simple for loop, right? And I just iterated through 1 through 7, and I used P2 out, whatever. But I'm just asking, is there a way to iterate through the hexadecimal values?
It should be okay.
Or
it should be, whenever you write 0x whatever, then the compiler, when it translates this, it will know this is a hexadecimal. So it will know if it's a number, just a number. Like, for example, you're writing 10, okay? So it will just make another step to convert it to decimal, or not need, no, sorry. It will just convert to the, so for example, if you write for I equal to 0, I less than, 10, I plus plus. Okay, so basically whatever you write will be converted to binary. and store somewhere, you know, in the RAMs, okay, in the memory.
Yeah,
So
but
if you write it like this, and the A is 10, okay, in the hexadecimal, what's gonna happen first? The compiler will see 0x, he will know that this is a hexadecimal, so it will convert it, okay, but using another algorithm he has, into also binary. So,
gotcha. Okay.
so it doesn't matter. If it doesn't work, then that's not your problem. It's a compiler problem. For some reason, you know, this compiler is not, you know, trained, we can say, to deal with hexadecimal values in a for loop. Okay, it shouldn't be, you know, a big
Okay.
issue
Yeah.
if it doesn't work.
Okay.
Okay. Okay, guys.
And Professor,
Yes.
for the lab 2, you didn't want us to do it in a safe coding format, right? You won't be graded if we didn't do it that way, or graded down because of it.
No, no, of course not. Lab 2, you mean the first assignment, which is the one that I was just explaining right now?
Yeah, because I did it. I just did it like an iteration, and I didn't do any safe coding on it. Is that
That's fine. Yeah, that's what I want in the first one. But if you do safe coding, it will be okay, of course.
okay?
Second, the safe coding is only required for lab 2. Homework 9. Let's be specific. Homework 9.
Okay, I was getting them mixed up. Okay, thank you.
Okay, guys, any other questions? You want me to look at any code you have?
Yeah, can you just check my code out, Professor?
Okay, I will go in a break room with Genesis. Okay, then I will go back if another if